When we engineer semiconductor devices at the angstrom scale, the exact distribution of charges at the boundary dictates how the entire system behaves. At these distances, a single layer of misaligned molecules can create a static potential barrier that determines whether electrons are blocked or accelerated across the interface. One of the most specific phenomena we encounter at these boundaries is an interfacial dipole. This is a microscopic, tightly bound separation of positive and negative charges sitting directly across an interface, like a metal meeting a semiconductor. This diagram shows what an interfacial dipole does to local energy levels. Because the opposing charges are separated by such a minuscule distance, they create a sharp, abrupt electrostatic potential step. There is an immediate jump in energy right at the boundary. But that abrupt step is rarely the only thing happening at an interface. We also have to account for band bending. Unlike this sharp jump of a dipole, band bending is a gradual potential variation. It spreads out over a much wider macroscopic distance known as the depletion width. This chart breaks down the physical causes. That gradual curve happens because a net space charge accumulates in the bulk material, which is governed by Poisson's equation. In real devices, these two distinct physical phenomena, the microscopic step and the macroscopic curve, almost always occur simultaneously. They overlap to create a composite energy landscape. To figure out what's happening on that surface, we typically bring in diagnostic probes to measure the surface work function or the vacuum level shift. The diagnostic issue with these macroscopic probes is that they only read the net result. They give us a single number representing the total surface potential change from the bulk material out to the vacuum. Here is the blind spot. Instruments reading that solid bottom block, the total measured shift, cannot tell if it came from a dipole step or band bending. That unified reading hides multiple overlapping variables, the pure dipole, band bending, and chemical artifacts. If you treat a surface and measure a work function change, you have not proven that you've engineered a pure microscopic dipole. To accurately quantify an interfacial dipole, we have to abandon the assumption that a single tool gives us the whole picture. We need a rigorous, multi-tool methodology to systematically subtract the variables we don't want. The first instrument in our analytical playbook is Ultraviolet Photoelectron Spectroscopy, or UPS. UPS works by firing ultraviolet light at the sample and measuring the exact amount of energy required for the highest energy electrons to completely escape the material and enter a vacuum. This chart shows a standard UPS spectrum. The critical metric is the secondary electron cutoff on the left. A lateral shift in this threshold directly tells us how much the sample's overall work function has changed. This checklist highlights a trap researchers often fall into. It is a myth that a work function shift is always an interfacial dipole. That shift can just as easily be caused by simple band bending or surface charging. UPS successfully maps the total outer boundary of our measurement. It gives us the combined shift, but leaves the internal distribution of charges completely unresolved. To solve for unknown internal variables, we bring in a complementary tool, X-ray Photoelectron Spectroscopy, XPS. Instead of looking at electrons escaping from the very surface, XPS allows us to measure core-level binding energies deep within the atomic structure. This energy diagram shows why that is useful. When the electrostatic potential changes, deep core energy levels shift rigidly, moving in exact parallel with the bands above them. By tracking these core levels, XPS isolates the exact magnitude of the gradual band bending curve. There is a diagnostic caveat here. Core-level shifts are not exclusively caused by electrostatics. They can also be triggered by localized chemical reactions, like oxidation. To avoid confusing electrostatic band bending with a chemical shift, you must use chemically stable core levels as your reference point. You have to verify no reactions occurred. Once stability is confirmed, XPS successfully isolates the macroscopic band bending. We now have the final variable we need to execute the math. Let's subtract the datasets. A UPS total shift of positive 0.80 electron volts minus an XPS band bending shift of positive 0.30 electron volts leaves exactly positive 0.50 electron volts, the pure, abrupt energy step caused solely by the interfacial dipole. This separation resolves a composite surface reading into a specific, defensible value for the microscopic dipole. Measuring an abstract energy level is only half the job. We must translate that energy step into the physical properties of the molecular structures. We start with a straightforward numerical conversion rule for electron charges. Exactly 1 electron volt of measured energy step equals exactly 1 volt of electrostatic potential step. So our isolated positive 0.50 electron volt energy step is accurately redefined as a positive 0.50 volt potential step. To link that macroscopic voltage to microscopic structural properties, we use the Helmholtz relation. This equation calculates how a layer of aligned molecules creates that exact potential difference. To solve for individual molecules, we need 2 known inputs, molecular density and the effective dielectric screening factor. Processing our voltage step through the Helmholtz equation with these variables gives the average perpendicular dipole moment, the electrical polarity of a single molecule, expressed in dBi. This calculation links a macroscopic spectrometer reading to a specific physical property, the individual dipole moment of each molecule on the surface. Let's review the complete methodology we just executed. First, UPS measures total surface shift. Second, XPS tracks the underlying band bending. Third, subtract band bending to isolate the pure energy step. Fourth, convert that shift into a voltage step. Finally, apply the Helmholtz relation to calculate the physical dipole density. The final takeaway is clear. True interface science cannot rely on single-tool assumptions. You cannot accept unverified composite shifts at face value. The value in interface science lies in deconvoluting a composite shift to verify its physical origins, rather than recording a raw change.